The ARIMA models, also known as the Autoregressive Integrated Moving Average models, are some of the most commonly used models in time series analysis. The ARIMA models can have several different types of components including AR or autoregressive component, MA or moving average component, and I or order of integration. Together, these components can be used to model and forecast various types of time series processes. A univariate ARIMA model has a dependent variable which is expressed in terms of its own autoregressions, that is, its own past values and disturbances. Such a model does not have any other variables, lags of other variables, exogenous variables, or a structural component. We will use the example of univariate ARIMA models to illustrate how different components of the model come together in an equation. Later, we will extend this understanding to include a structural component and exogenous variables to show an alternative formulation of the ARIMA models. First, let us take a look at a pure AR or autoregressive process. In the equation shown here, the dependent variable y is a function of its own past values or lags. The order of this AR model is given by ρ, which shows the number of past lags that are included in the model. For example, an AR1 model has only one past lag of the dependent variable y. Here, ρ is equal to 1 because y depends on its previous one-period value. This AR1 model is equivalent to an ARIMA 100 model because it only has one AR term. It has not been differenced and it does not contain any MA terms. Similarly, an AR model with ρ equal to 3 is known as an AR3 model. As shown here, an AR3 model will have 3 past lags of the dependent variable. That is, the dependent variable y depends on its previous 3-period values. Again, this AR3 model is equivalent to an ARIMA 300 model. If we are dealing with monthly data, this would mean that the current value of y depends on its values from the previous 3 months. The disturbance term mu in this equation is independently and identically distributed and normal with zero mean and sigma square variance. This implies that this mu is a white noise disturbance. Hence, in an AR model, we can simply use the past values of the dependent variable to forecast its values in the future. In a moving average model, the dependent variable is expressed as a function of past disturbances. The disturbances are also sometimes referred to as innovations in time series models like ARIMA and vector autoregressive models. The order of moving average is given by Q, which shows the number of lags or past values of innovations included in the model. For example, the MA1 model will have only one lag of innovations or disturbances as shown here. This MA1 model is also equivalent to an ARIMA 001 model because it does not contain any autoregressive terms and y has not been differenced. Similarly, the MA3 model will have 3 lags of innovations because Q is equal to 3, that is, the order of moving average is 3. Again, this model is equivalent to an ARIMA 003 as it has 3 lags of disturbances, no autoregressive lags, and y has not been differenced. As the name suggests, an ARMA process or model contains both autoregressive and moving average components. That is, such a model will have some autoregressive lags as well as the lags of innovations or disturbances. In the equation shown here, y is the dependent variable and it is a function of its own past lags and lags of innovations. As mentioned in the previous sections, ρ shows the order of autoregressive lags or the number of AR lags in the model. On the other hand, Q shows the order of moving average or the number of lags of innovations in the model. Together, we say that this equation represents an ARMA model of order ρQ or ARMA ρQ. Since we are not using differences, an ARMA ρQ model is equivalent to an ARIMA ρ0Q model. Let us consider the ARMA 11 model as an example. In the equations shown here, we have one lag of dependent variable y which represents the AR component with ρ equal to 1. We also have one lag of innovations or disturbances showing the MA1 component. This means that Q is equal to 1 here, which is the order of moving average. This ARMA 11 model with ρ equals 1 and Q equals 1 is also equivalent to an ARIMA 101 model. In the ARMA and ARIMA specifications discussed till now, we represented the dependent variable y in terms of its own past values or its own autoregressions. This means that we included the AR component as past values of y, that is, yt-1, yt-2 and so on. We can observe this in the equation shown here as we have past values of y in the equation. However, this is not the only specification of ARMA and ARIMA models. Alternatively, we can specify an ARMA and ARIMA model in terms of disturbances instead of past values of the dependent variable. Let us take a look at this formulation where we consider two equations in the ARIMA model. In the two equations here, the first equation is called the structural equation. This is because we can include other variables in this equation. The xt term here includes the constant, trends or other variables in the model. We can include any exogenous variables we want in the model using this xt term. The second equation is the equation of disturbances which contains the AR and MA terms. The disturbance of the first equation Vt is represented as the dependent variable here. It is a function of its past values, that is, Vt-1, Vt-2 and so on. These past values of Vt, which include Vt-1 up to Vt-ρ, are the AR component of the model. Here, we are including the AR component using only disturbances instead of past values of y as we did earlier. Still, the order of the autoregressive terms is shown by ρ. The disturbance mu is the white noise error in this second equation. The MA component is included as the past values of the innovations shown by mu, that is, mu-t-1 up to mu-t-q. The order of these moving average terms is shown by q. Using these equations, we can substitute the second equation into the first equation by replacing Vt. Therefore, we arrive at the equation shown here. Here, y is the dependent variable and it is a function of exogenous variables in xt, the AR component or the disturbances of the structural equation shown by lags of Vt, and the MA component shown by the lags of disturbances of mu. We have substituted the lags of Vt and represented them in terms of y and x variables. We can do this by manipulating the structural equation. This formulation of ARMA or ARIMA models is in fact the same as the previous specification. We considered a pure ARMA process in the previous specification without any other exogenous variables. So, if we remove the xt component and the exogenous variables from this equation, this formulation becomes equivalent to the earlier specification. Another way to write the general form of ARMA and ARIMA models is by using the lag operators notation. We often see the ARIMA models specified using the lag operators. This is because this notation allows us to show the general form of the ARIMA model in a concise way. In the lag operator notation here, ρ is again the order of autoregressive terms. Similarly, q is the order of moving average terms. Y is our dependent variable and xt contains the constant, trend or exogenous variables in our ARMA or ARIMA model. If we have to take the differences of the variables, the usual ARMA model becomes an ARIMA model. Till now, we have included the dependent variable y in its original form in the models. However, we have to consider the order of integration of y and take differences to make it stationary. The order of integration, usually represented by d, shows the order of differencing that must be taken to make the variable stationary. For example, if we say that d is equal to 1, it means that y becomes stationary after taking its first difference. Similarly, if d is equal to 2, the variable will become stationary after taking its second difference. An ARIMA model, therefore, includes not only the AR and MA components but also considers the stationarity and order of integration of the time series. In the equation shown here, we can see the usual AR component of order rho and the MA component of order Q. Similarly, the order of integration is shown by D, which represents the order of differences taken for the dependent variable y. Therefore, the order of this ARIMA model is rho, D, Q, and it is called an ARIMA rho DQ model. As an example, let us consider the ARIMA 111 model. The order 111 of ARIMA means that the model contains one autoregressive lag, first-order difference of y, and one moving average lag. We can see this in the equation shown here. Since D is equal to 1 in this ARIMA model, we have taken the first difference of variable y. As a result, our dependent variable now is delta yt, that is, the first difference of y given by yt minus 1. In addition to this, we have one autoregressive lag of the dependent variable which is shown by delta yt minus 1. We also have one moving average lag shown by mu t minus 1. Together, this gives us an ARIMA 111 model. If the ARIMA model contains exogenous variables, then they are often referred to as the ARIMAX models. These ARIMA and ARIMAX models are estimated using the maximum likelihood technique with the help of the Kalman filter and state space forms. In our discussion till now, we have seen that the ARIMA model contains three basic components, including the order of integration, AR, and MA terms. Hence, it is essential to choose the order of integration, order of AR and MA terms accurately in an ARIMA model. There are several techniques that can be used to determine the order of integration, order of autoregressive and moving average lags. We will discuss these techniques in later tutorials. Thank you for watching, and I will see you in the next tutorial.